Floating Point Systems was founded in 1970 by Norm Winningstad, which, by the way, is an excellent name. But by as early as 1971, they had several products out on the market that was adding floating point capability to several mini computers from the era. Floating Point Systems was so good at doing this that in 1976, they released the AP120B, an array processor add-on that added 12 megaplops? What would that stand for? 12 megaflops of supercomputing performance, which is out of this world to think about for 1976. For reference, in 1990, the 8486 could only do 1 megaflop. It was 1/10 of the processing power of the AP120B that preceded it by 15 years. However, that same year that the AP120B came out, the Cray 1 came out, which did 160 megaflops, which is not to throw shade at the AP120B. That thing is incredibly powerful. It's just Seymour Cray was an alien. That's the only thing that makes sense. Either that, he was a time traveler from the future. That dude built an unbelievable amount of performance in the mid-1970s. And actually, Cray's name is important here because that's going to come up a little bit later in our story here. So anyways, the Cray 1 was $7.9 million in 1976, but an AP120B was approximately $38,000. So yeah, you were only getting 10% of the performance of the Cray 1, but you were paying less than 1%. But the important part here is that they're both, the Cray 1 and the AP120B, array processors or vector processors. I think we're running into a little bit of a terminology dispute between computer programmers and mathematicians. Programmers call them arrays and mathematicians call them vectors. But they're doing the same thing in that they're working on a whole bunch of stuff at once. So let's imagine that I have 8 pairs of numbers and I want to add these numbers together. So if I were working on something like a PDP-11, I would have to do that one at a time. Add the first number together, store the result in memory, load the second 2 numbers together, add them, store it in memory, do it one at a time until I get to the end. But in an array processor, what we do is we load up all 16 of these values at once, and we do the addition all at the same time, completely in parallel. This is so much faster than doing it one at a time. And if that sounds familiar, that's because the GPU or graphics processing unit in your computer or cell phone that you're currently watching this on is essentially doing the exact same thing. But in 1976, 50 years ago now, oh my gosh. That's right, this is the 50th anniversary of the AP120B. That's pretty exciting, actually. So the AP120B was an absolute beast. Fast forward a little bit to about 1980, and they wanted to reduce the size of the AP120B because it filled up about 20 to 25 boards that required a phenomenal amount of power. And so they made use of some TRW multiplier chips and other large-scale integration techniques and got that down to about 10 boards and released that as the FPS 100. But due to the nature of the LSI chips that they were using, they couldn't run it at the same clock speed that they were running the AP120B, which means that speed dropped from 12 megaflops down to 8 megaflops. But architecturally, these two systems were identical, and I think you could use the same software suite on both systems completely interchangeably. But both the FPS 100 and the AP120B were pretty popular in the medical imaging field as well as the geologic field. Now the medical field, I get the FPS 100 and AP120B were both used on the very first CAT scanner from GE. So you're taking several slices of somebody's brain from several different angles, and you need a lot of vector math to reconstruct all those disparate images into something that makes sense for the doctor to read. But the geologic field, like I don't know, like I don't know anything about that field. So if you worked in that field, sound off in the comments below. I'm curious what you guys were doing that required a colossal amount of vector processing power to figure out. But the FPS and AP120B, it's important to note, are not standalone systems. They required a host system. They were pretty much just really hardcore math coprocessors for a host. The CT scanner, for example, was Data General Novas or Eclipses. I think in the geologic world, they used a lot of PDP-11s. Essentially, I think if you had a mini computer and you wanted a floating point systems box for it, Floating Point Systems would figure out a way to get that interfaced to your mini computer. They were a pretty small company and they were looking for people to sell boxes to. But the host system, each host system had their own unique way of representing floating point data. The way DEC did it was different than the way that Data General did it, which was different than the way that Prime did it, which was a nightmare if your system was a 38-bit system. So there was a lot of translation that had to go on between the host system and the floating point systems box. And this is going to be a problem for us a little later. But as the 1980s marched on, computing technology was progressing very rapidly. And floating point systems knew that single instruction multiple data was kind of limited in the supercomputing field, and they needed to push into something called MIMD, or multiple instruction, multiple data. So let's go back to our example from earlier. We have 8 pairs of values, and we want to do something with these pairs, but we want to do something different for each pair. I want to do an addition on one, a subtraction on the other, a division on a different one. We want to do an and on another. And so what we do is we load all 8 of these pairs up in parallel, set different operators for each one, and then do the math completely in parallel. And you can see that this adds a ton of versatility and speed to the system, which is exactly what FPS wanted. And they developed the XP series of processors. Now, initially, I think they had an XP22, but there's like no information out there on it. So ultimately, in 1985, they underwent a rebranding effort and released the XP32 processor. Now, the XP32 processor is interesting because it gives 18 megaflops of MIMD performance, but it needs the FPS 100 or AP120B to act as a control processor for it. So this is like a coprocessor for your main system. We're getting into exhibit levels of craziness here. But the really cool thing was that multiple XP32s could be stacked. So the FPS 5000 series was their rebranded initiative here, and that brought with it an FPS 100 paired with 0, 1, 2, or 3 XP32 processors. Now the FPS 5100 was essentially an FPS 100 with no XP32 processors. But an FPS 5400 would have been an FPS 100 with 3 XP32s to give you a total of 62 megaflops. Now, FPS did build a bunch of other stuff throughout this time. I've only really talked about the AP120B and the FPS 100, but they were building all sorts of really cool stuff. Notably, one of my dream machines is the FPS 164. They released this in 1982. It used a 64-bit word, had 8 independent pipelines, a 24-bit addressing space, and even had a D64 disk subsystem, which had 540 megabytes of storage. And it could support 6 of those for a total of 3 gigabytes of storage in 1982. Now, this, of course, even though it was like massive, still required a host system, and there was a variety of host systems that could be used with it. But my favorite is the VAX 11780. The 780 is a beast of a machine, and the FPS 164 paired with an 11780 would have been one of the most performant machines on the planet, and it certainly would have been nipping at the heels of Cray. Now, speaking of Cray, I mentioned that it was important to keep them in mind because they start to come into the picture for FPS here very soon. In 1988, FPS bought out Celerity Computing. Celerity was I think a competitor to FPS and kind of in this super mini field. And I think FPS in '88 was in dire straits, and they were really hoping that the buyout of Celerity would really help them get their footing back. But that wasn't the case. And in 1991, Cray Computing bought them out. Now, at the time, FPS was developing something called a matrix coprocessor. And then when Cray bought them out, it took the FPS team and kept them working on that matrix coprocessor, but it rechanged the name to the Cray APP. And I kind of consider this to be the swan song of floating point systems because it was their last proper design before the company had been completely absorbed into the fold of Cray. Once the Cray APP was released, floating point systems was, at that point, well and truly dead. who knew where their engineering team ended up? They all went their own individual ways. And well, here we are. Floating Point Systems is a defunct supercomputing company from the 1970s that built some really awesome stuff. Unfortunately, not a lot of that awesome stuff is still remaining. I only know of 8 systems that are surviving today. There's an FPS 100 up in the Northeast owned by my buddy Cully. There's an FPS 5100 over in Europe. There are 2 AP 120Bs in China. There's 2 more AP 120Bs up in Pittsburgh at the Large Scale Systems Museum. And if you've never been to the LSSM, go check them out. Dave McGuire is just an absolute riot, and all the volunteers there are doing amazing work. Then there is one AP 120B currently on eBay that the seller is asking $8,000 for, which is ludicrous and ridiculous. It's been for sale for well over a year, and he started at $16,000, and like, whatever, that one might as well not exist. And then finally, the 8th system that we know about is this FPS 3000 right here, but the FPS 3000 is a very weird machine. You'll notice that when I was talking about the history of FPS, I never once mentioned the 3000 series. This apparently was part of their rebranding effort, and it is an XP32 machine, but if you remember, I was saying that if you have an XP32 processor, you absolutely need an FPS 100 or an AP 120B to be the control processor for that XP32. Well, this can support 2 XP32 processors, but it doesn't need an FPS 100 or an AP 120B to be the control processor because it has a control processor built into it. And that is this card right here, which is a VersaBus single board computer. This has a Motorola 68000 on it, ticking away at 8 megahertz, has 128K of onboard dual port RAM, 64K of onboard ROM, 2 RS-232 serial ports, and that's all just on the local side. What makes this so unique is that it has effectively 2 buses. You have the local bus that touches the CPU, ROM, and RAM, and then you have the VersaBus that touches everything else. And that's what they're using to control the FPS 3000 and XP32 processors here. I think. There's zero documentation out there for the FPS 3000. Like nothing. We can't even find a mention of it anywhere on the internet. And we certainly don't have any schematics, not for a single one of the cards in here. So really, everything that I'm about to say about the FPS 3000 is just me taking kind of guesses based upon what I'm looking at here. We have the, what I'm calling XP32 bus, the VersaBus, and the host system bus. The XP32 processor, memory control, and 1 megabyte of RAM share the XP32 bus. Then the VersaBus translator and universal formatter go between the XP32 and VersaBus to provide all of the translation between those 2 different types of buses. And finally, the AP interface goes between the host system and the VersaBus. This is just like a complete guess. I have no idea if this is correct. This is just the only thing that makes sense to me based upon the ribbon cable layout on the front here and what cards are plugged into what. But since we don't have any schematics or documentation or anything really, this is pretty much just a stab in the dark. But what's stopping us from just plugging it in and seeing what happens? Like nothing really. Let's do that. Well, not nothing. We don't have any way to plug the thing into the wall. The original power cord was all rotted, so I cut it out. To make sure I have nice clean access to absolutely everything, let's remove the front grille, then flip the thing up onto its side, and then get to work routing a new cable. I'm going to use a heavy-duty extension cord that I'll sacrifice for this. I need to first remove all the remnants of the old cable, then I need to cut my extension cord to length, strip it back, then crimp on connectors for each of the 3 wires. After that, I'll snake it through the opening on the back, then route the live, neutral, and ground to their respective places, tighten it all down with the screws, and finally put in the strain relief grommet. With the cable sorted, I'll lay the machine flat again, then remove the side panel to gain access to all the cards. And for initial testing, we're going to remove every single card. These are all incredibly rare, and the last thing I want to do is explode them with a faulty power supply. Since we have all the boards out, let's just take a quick look at them one by one. Starting with this one, this is the main data, which I believe is 1 megabyte of system common memory. This is memory that the VersaBus single board computer should be able to put data into, and that the XP32 processor should be able to pull data out of. But otherwise, it looks like a pretty standard DRAM board. This is the MIM CTRL board, or memory control board. My guess is that this contains all of the DRAM refresh logic, as well as the CAS and RAS, and all of the selection logic that's required to keep the DRAM alive, as well as dictate where data is coming in from and where data is going out to. Now we're getting into some exciting stuff. The XP32 processor is divided up across two boards, an arithmetic unit and an executive unit, and this is the arithmetic unit. Notably, it has 3 Waytech chips on here. These are WTL 1032 and 1033, I believe. There's 2 of these Waytech adders and 1 of these Waytech multipliers, because we believe that this thing was optimized to doing fast Fourier transforms. And then the rest of this is just filled with a boatload of really fast static RAM. And these are the primary feeds into the Waytech arithmetic unit over here. And this is the other half of the XP32, the executive unit. And it has 2 of these absolutely stunning AM29116s. These are 16-bit bit slice ALUs, so our full 32 bits there. There's a collection of ROMs over here, which are going to store the executive unit microcode. That should be 2K by 80 bits wide. And then there's a collection of other stuff. I don't really know what's going on, but these 29116s, I'm absolutely in love with these. I would love to see these used in a homebrew someday. I think they're just absolutely stellar chips. This is the APIF, or Arithmetic Processor Interface. This is the primary interface to the host system. There's a collection of statograms over here that are all dual port, and all of these together create a 32-bit wide collection of static RAM registers. And essentially, I think what's happening is information is coming in from the host system into that static RAM, and then this is translating it and then shoving it out to the VersaBus. And I think that these dip switches here allow you to select different types of host systems, but unfortunately, we don't have any documentation, so we don't know what host system this one was set up for. This is the universal formatter, and it actually connects up to the VersaBus translator via these 2 little ribbon cables right up here on the top. So it's closely related to the next board as well. My best guess is that this is doing the formatting translation between the XP32 bus, which is 32 bits wide and uses a specific floating point format, and the VersaBus, which is 16 bits wide and uses a completely different format. This is the counterpart to that universal formatter that we were just looking at, the VersaBus translator. Again, there's, I don't really know what's going on here. There's 3 chips over here that are massive. These are MC68153s. I don't know what those are offhand. I'll have to look them up. But I don't know. It's a cool looking board. Lots of green baud wires going on here. So apparently 4 layers was not enough. And finally, we've come full circle to the Motorola built VersaBus single board computer with its absolutely beautiful 68K up here. The 2 ROMs here that is going to be controlling all of everything. I've actually dumped both of those, and they're over on the GitHub. I'll put a link in the description below if you're curious. Other than that, we don't really know a whole lot about this. There's no schematics out there. There is some documentation that explains how the bus layouts work and how it works as a bus master and whatnot, but that's really, I don't think that's going to help us all that much in understanding the FPS 3000. All right, let's throw some electrons at this thing and see what happens. The power supply is on a little hinged door here, and with it swung down, we can get a look at this insane 5-volt power supply. It generates 5 volts at 200 amps. That's 1,000 watts of 5 volts only. It's essentially an arc welder. Everything of importance has been removed. All that's left is a little bit of power supply logic all the way on the front there. And then obviously, you know, the power supplies. I am expecting this to generate 5 volts, plus 12 volts, and maybe minus 12 volts. And well, 5 volts is the big one. This does 5 volts at 200 amps. So I have no idea what that thing is going to do. But what we're hoping to see is there's a little AC on light on the back here that we want to see come on. We want to see that fan on the front come on, and then this fan on the back come on. And if all of that happens without anything catching on fire, we'll go through and check all the voltage rails, and then if that looks good, we'll start plugging cards in. So here goes nothing. Fan on the front came on. Fan on the back did not come on. We do have a little red light all the way over there, and our AC on light is flickering a little bit, but I think we can start checking some stuff. Okay, if we check the 5-volt rail here, nothing. 12-volt rail, nothing. Okay, so we're not generating any voltages. Well, the fan on the back isn't spinning, which is a big giveaway, but the biggest giveaway is that there's a on-off switch on the front here. So I don't know why the power supply fan is spinning. Maybe this primary power supply fan spins all the time, and then this one turns on the big one on the back or something. I don't know, but let's flip it and find out. Oh yeah, that's very loud. But we do have a little power LED on here. We got 2 red LEDs on the inside there. I think we're okay to start checking voltages now. Looks like we've got a nice, clean, and stable 5 volts. That's good. But when I check the plus and minus 12 volt lugs, there's nothing on them. And this was confusing to me. I started chasing down the lugs, and there isn't anything in this chassis that can actually generate plus and minus 12 volts. The little power supply card over here doesn't have any regulation stuff on it, and the lugs are not connected to any of the cables coming off the backplane. My theory is they would connect an external supply to these 2 lugs for testing, but since the VersaBus single board computer card is the only thing that uses plus and minus 12 volt, and it's only used for the RS-232 serial ports on the SBC, once they put the production ROMs in, they don't use the RS-232 ports anymore, so there's no need to have plus and minus 12 volts. That's annoying because it sent me down this weird rabbit hole, but also it means that our power is completely good because this is a pure 5 volt only machine. So let's get all the cards slotted back in and put some power into everything. Now we're getting exciting, everything's loaded up. There's a lot of things that could blow up. There's a lot of tail and caps on there, so I have no idea what's gonna happen, but let's flip the switch and hopefully no smoke. We have a host interrupt enable light on. I don't know if that's good or bad, but I didn't see any fire or brimstone, so I'll count that as a win. Well, it turns on, nothing went up in smoke. We get a host interrupt enabled light on the front and nothing else. It's completely and totally inert, but I don't think it's actually broken. I think this thing is sitting here at 100% functionality, raring to go, but we have nothing to tell it where to go or what to do. So in that regard, we have a couple of massive problems that I think might actually kill this whole project, unfortunately. The first is that we don't know what the host system originally was. The AP interface card that's in here is completely and totally undocumented. So we have no idea what it's set up for, although my guess is that it's probably a VAX or some other kind of 32-bit system. But it gets even worse, and that is that we don't have any software for this thing. No XP32 software is known to survive. It's all gone. I've scoured the internet for over a year now looking for anything about XP32 systems or FPS 3000 or 5000 stuff, and nothing. Without having software, what does that mean? Why are we dead in the water without software? Because we should be able to reverse engineer the instruction set potentially and feed data into this thing. But, well, the problem is with the XP32 itself. The executive unit has microcode stored in very high-speed programmable read-only memories, or PROMs, but the arithmetic unit uses a 128-bit micro word that is stored in RAM. So something needs to be loading the microcode into that RAM, so that way the arithmetic unit knows what operations it needs to run using those Waytech chips. And there's 2 paths about how that microcode could make it into the RAM. The first is that if we're incredibly lucky, the executive unit could be generating that microcode on the fly. The second is something far more terrifying, and that is that the software generates that microcode and loads it in. That's what the BOMEM high-performance vector processor does, and it uses a lot of the same chips, the same WATEC chips, the same AM29116. It's a very similar construction for that vector processor and this FPS 3000. Without the software, we may never be able to get this thing to do anything at all. So where does that leave the Floating Point Systems project? We know that we can't use the FPS 3000 and an FPS 100 together. The 3000 has its own built-in VersaBus control processor, so it's a completely separated thing, and I think we should probably dedicate this to a system that's more appropriate for it, like a VAX or something like that, which means that it's going to leave the PDP 1144 and we're going to focus on an FPS 100. This is a full board set for an FPS 100. All 11 boards that we need, it's complete. We have 2 data pads here, then we have a floating adder and a floating multiplier over here, then we have our P1, P2, P3. This is going to build out the processor for it. We have our main data memory as well as table memory over here that's full of a bunch of ROMs, and then finally we have our PDP-11 interface card with our formatter card. With these 11 boards, we should be able to get a fully complete FPS 100 up and running, with the exception of a backplane. These all have to connect to each other, and it's not a universal backplane. Essentially what FPS did was they created a netlist and they had a machine that would do all the wire wrapping for them. So we're gonna have to recreate that, only without a wire wrap machine. Also, we gotta figure out how to build a box for this thing. All I have is this set of boards right here. So I gotta build a box, I gotta find a power supply for it, I gotta get all that wired up, and then we gotta build a backplane from scratch. So we got a serious journey ahead of us, but this is now a hardware journey because we have all of the we have most of the software for a FPS 100, and it's all meant for an RSX 11M operating system on a Unibus PDP-11, which we happen to have set up over there. So the only thing holding us back from doing real deal supercomputing shenanigans in this room is a new backplane. And that's what we're gonna get to work on in 2026. And I hope to be doing some vector processing before the end of the year. So I'm pretty excited about that, even though this is going to be an extremely difficult journey. So I wanna thank you all so much for watching, and I hope to see you in the next one. That's a lot of work.